What I want to do today is to introduce to you what I think is the world's most powerful microscope and also the world's most powerful telescope. Now, when you think of microscopes or telescopes, you think of sort of peering through some eyepiece down like that, or peering through some sort of eyepiece up like that. You probably don't think of what you see on this slide here. This slide is a picture of the region of Geneva in Switzerland. Those things at the back there, for those of you who are native Illinoisans, those are mountains. And, okay, so that's the Mont Blanc. This is downtown Geneva over here. This is the local airplane accelerator, otherwise known as the airport runway. And here, outlined in red, you have the location of our microscope stroke telescope. So it's a particle accelerator. It's about 27 kilometers in circumference, and on average, it's at a depth of about 100 meters. So in fact, from your airplane, you don't see very much. You might see one or two surface buildings, for example, this one over here, but most of the real action takes place about 100 meters underground. So what I would like to do in the course of this talk is explain why we've been building this thing, what science it is supposed to do, and I'll discuss also the progress that we've been making in this project, and in order to forestall some questions, what use it all is. So I thought I'd start off by sharing with you a reproduction of a painting by Gauguin, which I had a copy of the wall on my office when I was a graduate student, embarrassingly many years ago. So what these people here are asking are very fundamental questions. Where do we come from? What are we? Where are we going? And what I would like to argue is that the project, the Large Hadron Collider at CERN, which I showed you briefly on the previous slide, that the aim of this project is precisely to address these questions from the point of view, obviously, of a physicist. Concretely, what we try to do with projects such as our accelerator at CERN and the Fermilab accelerator just outside Chicago is we try to understand what the universe is made of. We also hope to understand the evolution of the universe, which could enable us to understand where we come from. And maybe we'll also learn a little bit about what might happen to us and to the universe in the distant future. So that's the aim of the project, which, as you see, is a connection between the physics of the very small, the microphysics, and the physics of the very large, macrophysics and cosmology. And I'll try to bring out those connections between the two during the course of this talk. So in our journey towards the very small and towards the very large, we're going to meet a number of ideas which I would just like to mention to you as we get started. So one of the issues, in fact, the primary motivation for building these large particle accelerators is to understand what matter is made of. And in fact, we have a theory for how the visible matter in the universe is constructed, which I'll describe very briefly later on. This theory has certain things which are missing elements which we hope to find with the LHC. Also, we think that there is physics beyond what we call the standard model of particle physics. For example, the astrophysicists and the cosmologists tell us that something like 80% of the matter in the universe is some form of invisible so-called dark matter, which they can't see with their telescopes. But I would claim that we, with our telescope, do have a chance of seeing this. As I mentioned, we hope by this sort of study of fundamental physics to cast some light on the way in which the universe evolves. This is because when we make our collisions in this sort of particle accelerator, we are reproducing the sorts of collisions that took place when the universe was a fraction of a second old. And I'll explain this in a little bit more detail later on. one of the sorts of issues that we can address in this way is where the matter in the universe originated. You look around you, you see matter. You see radiation. You don't see antimatter. Now, we physicists know that every matter particle is in principle accompanied by an antimatter particle with very similar but opposite properties. Where did all that antimatter go? Maybe laboratory experiments can answer that question. The universe is kind of big and old. How did it get to be that way? Maybe by understanding the early history of the universe better, we can answer the question. We know that there are 3 dimensions of space. Are those all that there are, or are there perhaps more dimensions of space? This is a possibility which is suggested in many theories of microphysics, and that might also cast some light on the early history of the universe. So the Large Hadron Collider, the LHC, the project which I showed you on my first slide, its principal jobs are to ask and hopefully answer at least some of these questions. So let's start off by looking inside matter. Now there's sometimes a misconception which I'd like to clear up. What we study with these particle accelerators is not some sort of abstruse stuff. We're actually discussing the structure of matter, the same matter that you and me and these roses are made of. And I think that we physicists sometimes fail to convey the wonder of the fact that all the visible matter in the universe is made up out of the same very limited number of constituents, which is really quite remarkable. All the variety of stuff that we see in nature is made up out of a few very small constituents that we can study in the laboratory. So you all know that matter is made up out of atoms. Atoms consist of electrons circulating around nuclei. You can think of nuclei as being a little bit like the sun in the center of an atomic solar system. Now, in the first half of the 20th century, it was realized that those nuclei could all be made out of 2 particles, the proton and the neutron. And for a while, physicists thought that protons, neutrons, and electrons were basically all the elementary particles that there were. In fact, what happened in the second half of the 20th century was people first of all realized that protons and neutrons were not alone. There were many other similar types of nuclear particles. And then they understood that these nuclear particles could all be understood in terms of a very small number of particles called quarks. So the frontiers of our current knowledge are electrons and similar particles, and inside the nucleus, quarks and the particles, the gluons that hold them together. So our job now in particle physics in the 21st century is to go beyond what was achieved in the 20th century and try to understand in more detail just exactly what these fundamental particles are, and also to understand the forces between them. Some of the forces are relatively well known, for example, electromagnetism, which holds those electrons in orbit around the atoms. Gravity, of course, that's also well known, but some of the other forces may not be so familiar to you. So I thought I would just briefly review with you 1 or 2 aspects of the search which revealed to us, or the searches that revealed to us some of these elementary particles. In fact, the first elementary particle to be discovered was the electron. It was discovered right towards the end of the 19th century. In fact, it's sort of ironic that just around the time when physicists finally got themselves convinced that matter was made out of atoms, Thomson, whom you see here, discovered that actually atoms were divisible and they had these electrons inside them. The apparatus that he used to show this is much like a traditional TV set. I used to be able to omit the word traditional, but nowadays, with all these plasma displays and so on and so forth, I have to sneak in the word traditional. So the old-fashioned TV sets had this sort of conical thing sticking out the back. And this conical thing sticking out the back was actually a primitive particle accelerator. It would do the same sort of job that Thomson's apparatus did. It would take an electron out of an atom and then accelerate it using electric and magnetic fields to strike the screen at the front. And then the image on the screen, well, that was what you saw. So particle accelerators are much like that. We extract electrons or protons out of the interior of atoms, we accelerate them, and then we either hit a fixed target or we hit these particles against each other and try to see what is produced. Now, many of the different types of elementary particles were first discovered in the cosmic radiation. As you probably know, the Earth is bathed in energetic particles coming from outer space. In fact, these were discovered a little under a century ago by Mr. Hess here, who's going up in his balloon. He went up in his balloon and discovered that up in the upper atmosphere there were all these charged particles raining down. Subsequent experiments showed that these particles produced many other different types of particles. The study of these things was a little bit haphazard in the first half of the 20th century, which is why sometime around the turn of the century, big accelerator laboratories were first constructed. And in particular, CERN, the European laboratory where I work, was founded in 1954 in order to study in more detail, under controlled laboratory conditions, the natural phenomena of elementary particles. Let me just mention one particular discovery that was made initially in cosmic rays and then followed up in particle accelerators. So I already mentioned antimatter. So this was actually first predicted theoretically about 80 years ago, and shortly afterwards the first particles of antimatter, the positrons, the antiparticles of electrons, were discovered in cosmic rays. And here is Anderson with his apparatus that he used to discover these first antimatter particles. So these things have the same mass, but the opposite charge as conventional electrons. Now, for many, many years, the existence of antimatter was a sort of academic curiosity. But in fact, now they're used regularly in medical diagnosis, and this is actually something that I'll come back to towards the end of my talk. So that's just an example of how even totally abstruse discoveries might actually turn out to be useful for real people like you, as opposed to physicists. Okay, so these studies, first of all with cosmic rays and then followed up in more detail with particle accelerators, led us to what we call the standard model of particle physics. And I'll just summarize it very briefly on this slide. So what you see here are the fundamental particles of matter. So we already met the electron. For a reason which we don't understand, the electron is followed by two heavier particles, very similar but just larger masses. Over on the left-hand side here, we have the quarks. These are the constituents of nuclear matter. In fact, the regular stable nuclei could be made up out of just two different types of quark called up and down, but in cosmic rays and in collider experiments, 4 more quarks have been discovered. We don't know why there are 3 electron-like particles. We don't know why there are 6 quarks, and that's one of the big mysteries that, well, we might get some insight from the LHC. The bottom half of the slide, you see the 4 fundamental interactions. Gravity and electromagnetism, and then 2 forces that act inside the atomic nucleus. The strong force, which holds nuclei together most of the time, and the weak nuclear force, which causes some particles to decay. It's actually the interplay between these 2 forces which enables the sun to shine. So although we don't necessarily like the idea of nuclear forces, in fact, they're absolutely essential for our existence. So what you see on this slide contains enough information when you go through the physics, go through the maths, to explain all the visible matter in the universe. And for that reason, I like to refer to it as being the cosmic DNA. So I said cosmic DNA. In particular, all the stuff in the universe, the visible stuff in the universe, is made out of what you saw on the previous slide. So here's a picture of the evolution of the universe. We're up here somewhere on an insignificant planet orbiting an insignificant star in an insignificant galaxy among 100,000 million other galaxies in the universe. So what we know is that as time goes on, the universe is expanding. The laws of physics, which we understand, enable us to describe what happened back in the very early stages of the Big Bang. Now, I hasten to say, not back to time equal to zero. Time equal to zero, in fact, the physics that we understand breaks down. So we're modest people. We're not going to go back to time equal to zero. We're going to go back to just an infinitesimal fraction of a second after the Big Bang. So very briefly, this is a history of some of the important events in the evolution of the universe. So somewhere around 300,000 or so years after the Big Bang, that was when atoms were formed. Before then, the universe was so hot and so dense that matters could not exist. They just dissolved instantaneously. So atoms contain nuclei. In fact, there weren't any nuclei at all when the universe was less than 3 minutes old. They also were dissolved by the very high temperature and pressure. Nuclei are made out of protons and neutrons, but if you go back before the universe was a microsecond old, then even protons and neutrons didn't exist, and what you had was some sort of soup made up out of quarks and other elementary particles. Now, what I've described up to now is what we think we can describe using the known laws of physics. What the LHC will be able to do, we think, is to take us back to a picosecond, so that's a millionth of a second after the Big Bang, and reveal to us the physics that was going on at that time. For example, where the masses of the elementary particles came from, and many other questions. So I talk here about the masses of elementary particles. This is one of the key issues confronting particle physicists today, and so I'd like to take a little bit of time out to describe this to you. So the question here is, why do things weigh? Well, some of you may not have gone through high school yet, but those of you who did go through high school surely remember that Newton taught you that weight is proportional to mass. And even if you haven't been through high school yet, I'm sure you know E equals mc squared. Einstein told us that energy is related to mass. However, these two honorable gentlemen unfortunately forgot to tell us what mass actually is. They related other things to mass, but they didn't give us a fundamental explanation of where the mass comes from. And that's where this distinguished gentleman comes into the picture. This is Peter Higgs, theoretical physicist who has a theory for where the mass comes from. And here's his theory on the blackboard behind him there. And memorize it, because there'll be an exam as you leave the room. There won't, but... So according to his theory, there is a particle, which we call the Higgs boson, which is at the origin of the masses of all the elementary particles. And obviously we want to find this particle because it plays such an important role, and so it's become, in some sense, the physicist's holy grail. Now, I recommend that you look up Higgs boson on Google, because you will find that Higgs boson is also a jazz musician. I might mention that many of the ideas that Mr. Higgs has been playing around with were behind one half of last year's Physics Nobel Prize, which went to Mr. Nambu, who is a local boy. He works up at the University of Chicago. Now, I'd like to try to give you some idea of the way in which the Higgs does its job. And since we're out here in the middle of the prairies, and since you still remember winter, let's think of a snowfield, an infinite snowfield stretching out featureless into the distance, completely uniform. This is the Higgs field, as we call it. Now let's consider a skier skimming across the surface of the snowfield. Doesn't interact with the snow, just skims across the top. This is like a very fast-moving particle without mass. Think, for example, of the photon, the particle of light. Light always travels at the speed of light. Now let's consider a snowshoer. So the snowshoer sinks into the snow, goes a bit more slowly, travels at less than the speed of light. That's like a particle which does have mass, the electron, maybe. And then finally, let's consider somebody who doesn't have any snow equipment at all, just hiking through the snow with boots on, sinks very deeply into the snow, moves very slowly. That is like a particle with a very large mass. So this is just a sort of caricature of the Higgs idea, a sort of universal medium. Whether you have a mass, how much mass you have, depends on whether and how you interact with this universal medium. Now, if you think snow, what is snow made up out of? What is the quantum of the snow field? Well, that quantum is the snowflake, also known as the Higgs boson. The Higgs boson can be regarded in some sense as the snowflake of this universal Higgs field, and the job of the LHC is somehow to kick up the snow and identify this particle of the Higgs snow field. Finding this particle, if it exists, would complete the standard model of particle physics. But as I mentioned earlier on, we know that the standard model is incomplete. There must be something else. In particular, there has to be something to explain the dark matter. So what the astrophysicists tell us is that there's perhaps 5 times as much invisible dark matter as there is visible matter. So here's a typical galaxy, pretty much like our own, spiraling around. And all over here, there's the dark matter, which you can't see, or at least the telescopes can't see it. Maybe we can with our particle accelerators. How do we know that this stuff is here? Well, there's a whole bunch of different ways in which the astrophysicists have convinced themselves and us that this dark matter must exist. As I mentioned previously, those galaxies are spiraling around like that. Now, in fact, they're spinning around so fast that they should actually fly apart. They don't. Why don't they fly apart? Because there must be some additional force, gravitational force, which is holding them together. Gravitational force which is generated not by the particles that we see, they aren't enough, but by these additional dark matter particles. There's other evidence that these dark matter particles have to exist. For example, we can see blobs of hot gas. This hot gas has very high pressure. It tries to expand, but it's held in place by what? By the gravitational field created by these dark matter particles, we think. In fact, people have even seen galaxies without stars. So here you do not see the galaxy without stars. So how do you know that that galaxy is there? Well, because you look at the light coming from the galaxies behind, and it's bent by the gravitational field of the dark matter that you cannot see. There's many other observational reasons for thinking that this dark matter exists. I would claim, I'll show you an example later on, that the LHC could discover the particles of this dark matter. Now, the universe contains visible matter, but none of this antimatter, which was postulated by Dirac, whom you see in these mirror image pictures over here. Now, when the antimatter was first of all discovered in cosmic rays, then it was studied in detail in particle experiments, it was discovered that matter and antimatter don't quite behave equally and oppositely. Why not? Well, there's a description of how this can happen in the Standard Model. This description was actually provided by Kobayashi and Masukawa, who share the other half of the 2008 Nobel Prize. Could this very small difference between the behavior of matter and antimatter be related to the fact that the antimatter has apparently disappeared from the universe, which only contains matter? Well, it's possible, but the matter-antimatter difference, which has been seen in the laboratory and which is contained in the model of Kobayashi and Masukawa, would not be sufficient to explain the dominance of matter in the universe today. That would require physics beyond the Standard Model. It's physics that potentially the LHC could discover. Finally, on my list of fundamental questions, let me mention the search for a unification of all the fundamental interactions. So this was Einstein's dream. I find it remarkable. I know how old Einstein was in this picture. He was 6 years old or something like that. But you can see in his eyes the same sort of sad expression that he had 70 years later. Sad? Well, sad because he didn't make a unified theory of the fundamental interactions. He tried. This is his last blackboard, but no banana. Now, he played with various ideas for how you could construct such a unified theory. One of those ideas was that there might be additional dimensions of space. Normally we think there are just 3 dimensions of space, up, down, front, back, and sideways. But if you look deep inside matter, it's possible there might be additional dimensions of space. And this is very popular in some of the current theories of unification based on string theory. And this is something which maybe we could find with the Large Hadron Collider, the LHC. So I've described to you some of the motivations that we have for making the LHC. But before describing the LHC itself, I would just like to share with you a little bit of personal experience. Back in 1982, Mrs. Thatcher, the Prime Minister of England, came to visit CERN. And so I was introduced to her. And she asked me, "What do you do, young man?" So I explained that I'm a theoretical physicist, and my job is to think of things for the experimenters to look for. And I said, then hope they find something different. Now, Mrs. Thatcher liked things to be exactly the way that she said. So she said, "Wouldn't it be better if they found what you predicted?" So I told her that, well, if you only found what you predicted, then you wouldn't really feel that you were learning anything. The really exciting stuff is the stuff that has not been predicted. So although I've described a lot of things that we think we might find at the LHC, what I really hope is that we're going to find something completely different. Okay, so here is the microscope stroke telescope itself. So this is a view in the tunnel of the LHC. I remind you, here we are something like 100 meters underground. And as you go around the 27 kilometers circumference, you pass by 1,232 magnets contained in these blue tubes here. Now, when the LHC is operating, in each direction around those magnets will travel several thousand billion protons. Each of those protons will have approximately the energy of a fly. It'll be traveling extremely close to the velocity of light, and so it will go around this 27-kilometer ring 11,000 times per second. Now, what we hope with this circulation of these beams, two beams in opposite directions, very intense beams, we hope that we will make something up to a billion particle collisions per second, and among those billions of collisions, we hope we're going to produce the Higgs boson, dark matter, and something which we haven't predicted. So this is the official list of the things. Origin of mass, dark matter, the primordial plasma that filled the universe when it was a fraction of a second old, and to understand the matter-antimatter difference. So a few gee-whiz slogans about the LHC. So it's the emptiest place in the solar system. Inside these magnets, you have two pipes that the particles go around. They have an extremely high vacuum. In fact, that vacuum has a similar pressure to interplanetary space and 10 times lower than the pressure of the atmosphere of the moon. Of course, the moon doesn't have an atmosphere. Nevertheless, there is a small amount of gas around the moon, but we've got even 10 times less pressure than that. The magnets of the Large Hadron Collider are superconducting magnets cooled to a very low temperature. In fact, the temperature, these are parts of the cooling system, by the way. That temperature is even lower than outer space. The LHC operates, or will operate, at a temperature less than 2 degrees above absolute zero, whereas outer space is at a temperature of 2.7 degrees above absolute zero. So, well, I don't know whether size matters, and certainly the universe is a lot bigger than our accelerator, but the LHC is cooler than the universe. So, here is a cutaway view of the LHC. So, here again is our airplane accelerator over here. Here is the LHC ring in which all those particles are going to be going around. Coincidentally, the energy of the particle beams is going to be roughly the same as that of a flying airplane. Now, around these... Ooh. That's not me. Keep your fingers crossed. Somebody doesn't like our experiments. Okay. They're going to switch to another computer. Apparently got a problem connecting.
It's more exciting when things happen you didn't predict.
Now you're taking me too literally there. So are we ready to roll? Okay, so at 4 points around this ring, there are places where particles collide. Okay, the tool works. So 2 of these called Atlas and CMS, that's where we're going to be producing, hoping to look for things like the Higgs boson and dark matter. This experiment over here is going to be looking at the primordial plasma, and this one over here is going to be looking at differences between matter and antimatter. So when we make collisions in the LHC, if we ever get to see the next slide, yes, there we go, those collisions produce for a very, very brief instant in a very, very small space what is perhaps the hottest place in the galaxy. In fact, we estimate that within a very, very tiny volume, the temperatures are perhaps 1 billion times higher than the heart of the sun. Of course, this is only in an incredibly small space, and almost immediately that we make the collision, the particles spray apart, as you see in this picture, and not very much energy is released. After all, the energy of each particle is like the energy of a fly. So, no, don't worry, we're not actually going to blow the planet up. So here are just a few gee-whiz numbers for the LHC. Circumference almost 27 kilometers, depth about 100 meters. Another one coming. Temperature minus 271 degrees. The energy of each particle, particle physics units, it's 7 TeV. In everyday units, that's equivalent to the energy of 5 billion AA batteries connected end to end to accelerate the particle. That corresponds to the energy of a fly, and the energy is something like 7,000 times the rest mass energy of an individual proton. So the whole energy of the proton beam, as I already mentioned, is comparable to that of a flying airplane. Now, in order to produce those billions of collisions, we focus the particles down so that the beams are thinner than a human hair. And the whole thing cost, well, the material pieces cost something like $3 billion, to which you probably have to add a similar amount for the salaries of the people who assembled it, and then there's a whole bunch more for the experiments and so on. So, you know, when you add everything up, you're probably talking about not much change from $10 billion. Now, a year or so ago, I might have been embarrassed to mention $10 billion. But not anymore. Okay, so this is an example of one of the LHC experiments. This is the ATLAS experiment, which, in fact, the University of Illinois is involved with. So it's kind of big. Here's a person to show you the size. It's almost 50 meters long, 25 meters in diameter. It weighs almost as much as the Eiffel Tower. So this thing has, it's sort of designed like a cylindrical onion, and each layer of this detector is optimized for detecting a different type of particle. So it's a pretty complicated thing. It was put together by over 2,000 scientists and engineers from something approaching 40 different countries. Pretty complicated. It has, somebody calculated, several times the number of components of a Saturn V moon rocket. So perhaps not surprising that it doesn't always work perfectly, but we'll come back to that. So this is a sequence of pictures showing the assembly of ATLAS in its underground pit. So the head of ATLAS used to like to compare this to putting together a 45-meter long ship in a 50-meter long bottle 100 meters underground. These silver things that you see here with the orange stripes, these are parts of the magnet system. And this is the final iconic image, which you must have seen a dozen times already, of some guy for scale showing you the ATLAS detector. In fact, if you go there now, you can't see inside because there's particle detection chambers all around the outside. It's basically all hermetically sealed. So you're just going to have to live with this picture. Now, I mentioned that this was put together by over 2,000 scientists from nearly 40 countries. In fact, the total number of scientists working at CERN on this and related experiments is something like 9,500. And well, here you can see the variety of countries that are involved. We've got Iranians working with Americans. We've got Palestinians working with Israelis. We've got Indians working with Pakistanis. And we've even got the English working with the French. So in order to permit all these scientists to work together, this guy here, Tim Berners-Lee, invented the World Wide Web. It was invented 20 years ago, almost exactly, in order to enable physicists to share their data. And he was working at CERN at the time, and nobody at CERN, least of all Tim, realized what a revolution in human society it was going to make. So the next time when you download from that pornographic site, please remember the guy who made it possible. What we're doing now in order to analyze the gazillions of data that are coming out of the LHC is to construct the largest computer system in the world. It's going to connect together the equivalent to something like 100,000 PCs in order to do decentralized distributing grid computing. And well, we think this is something which is going to be useful not just for particle physics, not just for other sciences, but also for other aspects of human life, although we can't actually tell you, immediately what it's going to be useful for, apart from scientific purposes. So what you're going to do with all those computers? Well, you're going to be looking for things like this. This is a simulation of a Higgs boson event. So you have to imagine that two protons have collided, one coming down there, one coming up there, produce a bunch of particles. Among them is the Higgs boson. The Higgs boson is unstable, and in this simulation it decayed into four other particles, an electron-positron pair that you see over here, and a pair of muons that you see over there. So one of the LHC collaborations is all ready for this and other discoveries. They've already got some joke papers prepared. This is a little bit optimistic if you look at the date over here, but maybe later on this year or next year it could turn out to be reality. In fact, in this joke paper, they were planning on detecting supersymmetry, planning on detecting dark matter particles. So the whole point about a dark matter particle is that you can't see it, right? It carries energy away from the event. So how can you tell that it was there? Well, it's a little bit like that Sherlock Holmes story where the most important clue was the dog that did not bark. So here you've got the picture of the detector. Some parts of the detector do bark, but this bit over here did not bark. It didn't detect any particles. So the interpretation would be that dark matter particle or particles were produced and went out through that part of the detector. So that's what people are going to be looking for. Of course, they have to be able to distinguish between that and just some, I was going to say wardrobe malfunction. No, detector malfunction. Now, here's another thing which they're going to be looking for. In some of those scenarios with extra dimensions of space, gravity, which we normally think of at the elementary particle level as being an incredibly weak force, could actually become strong. And it could become so strong that when you collide two protons, two of the quarks inside them might actually fabricate a microscopic black hole. Remember, this black hole has an energy comparable to that of two flies. Right? So this is not a big astrophysical black hole. This is a tiny little microscopic black hole, which, according to the crazy theory that says these things might be produced, would also be extremely unstable. So the way you would look for such a thing would be looking for the particles that are emitted by this thing. And here you see a simulation of what such an event might look like. Now, people have heard about black holes, and there have been a few scaremongers who said, ooh, we're going to destroy the planet. This, to use the polite word, is rubbish. Okay. Cosmic rays with much higher energies have been hitting the Earth for billions of years. They've carried out the entire LHC experimental program 100,000 times on Earth. as I speak, every second, the entire LHC program is being repeated something like 10 billion times per second, somewhere in the universe. The Earth, the Moon, the Sun, the stars are all still there. No need to worry. There is absolutely no conceivable cause for concern. The LHC is not going to destroy the planet. I couldn't resist showing this picture here. This is taken with a camera phone in a London railway station the day when we started up the LHC, and the local evening newspaper had this headline that the world survives the Big Bang when the LHC was started up. This is actually a picture of when we started things up on September the 10th. This is the control room. Everybody looks very excited and happy, except for this guy. He looks kind of young. So we achieved true fame. We featured for one day on the Google portal page, and something like a billion people watched at least some part of the LHC startup on TV. It's not often that a scientific event is watched in real time by a billion people. I'm sure that most of those billion were probably looking to see whether they're going to get blown up by a black hole. But anyway, so this is what they saw. So this little splodge of light is when the particle goes through a screen on its way around the accelerator, and the second splodge is when it comes back having gone one complete rotation. So this was the great eureka moment. This is when everybody in the control room burst into applause, and the journalists were kind of baffled until they realized what was going on. So in those preliminary tests, we didn't actually collide the beams, but we did collide the particles in the beam with beam stops in the tube. That produced showers of particles which then went through the detectors, and in that way we were able to verify that the detector actually works. So here's one event where the Atlas detector, the one the University of Illinois is involved in, lit up like a Christmas tree when particles came through. And this is one of our collaborators. He's a sort of example of CERN internationalism, by the way. He was born in Argentina, studied in Chile, worked for many years in Germany, is now attached to a university in Israel, and is very active bringing Palestinian students to CERN. Anyway, so in this picture, he's very glad that the thing is working. Unfortunately, didn't work for very long. A few days after we started up, there was an electrical fault in the connection between a pair of these magnets. This electrical fault heated the connection up. That heating melted the connection. It broke the vacuum pipe. It broke the cryostat. The liquid helium became gas. Big problems. So these are now being repaired. The last damaged magnet has been put back into the tunnel, and later on this year we will restart operations. Considerably warier and wiser, I expect. I said that lots of people watched this on TV. This was actually the lone LHC protester who is pictured here outside the press room at the LHC startup, and somebody very kindly provided him with a journalist's coffee cup and a sandwich just to keep him going. So just to finish off, I might say a few words about what's the use of all this. Well, I would say that understanding the way the universe works is a good thing in itself. But in the process of acquiring this knowledge, you develop technologies which can then be useful, like, for example, the World Wide Web. And also the fundamental discoveries that you make may themselves turn out to be useful later on. Let me give a few examples. So, particle accelerators. there are tens of thousands of particle accelerators around the planet. Something over 90% of those, if not 99% of those, are not used for fundamental science. They're in hospitals, they're in industrial companies, they're used for practical purposes. For example, more than a half of the accelerators in the world are used for medicine, either producing isotopes that are used in medical diagnosis or used for cancer therapy. We don't only develop accelerators, we also develop detectors for seeing what these accelerators produce. And many of these detector technologies are now used, also have potential uses in medical diagnosis. I might mention the technique of positron emission tomography, or PET. This is one of the most common techniques used for localizing and studying cancers, and it actually depends on antimatter. Positron, that's the antiparticle of the electron. And not only does it use antimatter, but you also use an accelerator in order to produce this isotope, and then once you've produced it, the signature is detected by modern particle detectors. Did I remember to mention the World Wide Web? Yeah, maybe I did. Okay. Let me mention perhaps finally one or two other examples. On the left here we have Maxwell. He was the guy who formulated a theory of electricity and magnetism, which of course underlies all those mobile telephones that you all have. This guy you recognize, right? So he came up with the theories of special and general relativity. What you may or may not know is that this actually plays an essential role in GPS satellite navigation systems. The signals which are used to navigate with come from satellites. These satellites kind of high up, kind of traveling very fast. And you have to understand the theory of general relativity and the theory of special relativity in order to calculate where you are. So if you use your GPS system to get home this evening, please thank Einstein for getting you there. Another spin-off of physics at CERN is this movie that will be coming to a cinema close to you in the near future. So Angels and Demons is actually starts off at CERN, where the LHC is supposed to be producing large amounts of antimatter. Well, it won't actually do that, but okay, it makes a good story. And here is a meeting of the CERN Council. Well, it was taken from the movie, so I thought that was what it was. Maybe it's not that. This is actually a picture of Tom Hanks and his co-star and the director of the movie, who visited CERN a few weeks ago. And this is another still from the movie, which actually I think looks surprisingly authentic, doesn't it? Yeah, it's pretty convincing. Anyway, I'm sure that when the movie actually comes out, there'll be another hurricane of publicity about particle physics and antimatter and CERN and the LHC, and you will be the envy of all your friends, because you will be able to tell them what it's all about, and you'll be able to explain to them about antimatter. Okay, well, that finishes what I want to say. I hope I've convinced you that the LHC is indeed not only the world's most powerful microscope for looking inside matter, but also a telescope for seeing things like dark matter that regular telescopes can't see. So, in fact, the LHC is the opposite of going back to the future. It's actually going forwards to the beginning of time. Thank you. Surely, yes. And, well, like I told you, I sincerely hope that the LHC will not find any of the things that have been predicted, and that, in fact, it will find something completely unexpected. If you look back through the history of accelerators, often they have been built in order to do one thing, but actually they become famous for doing something completely different. For example, there was a very famous accelerator at Berkeley in the 1950s that was built in order to manufacture the antiproton, and it did, but that was not what it became famous for, and in fact led to a completely new vision of what we meant by an elementary particle. There was another accelerator which in the 1960s at Stanford in California fired electrons into protons, not expecting to see very much, and it discovered quarks. So I think there's a very good chance that something completely unexpected will emerge. But if I knew what it was, it wouldn't be unexpected.
We need to wait till the microphone gets to the so because we're recording the question.
I've had some physics students who years ago left the field of physics when the big project in Texas was shut down because there was no funding to sustain it. Will the CERN efforts go beyond anything that might have been achieved by the Texas whatever it was called?
SSC, yeah. Basically, the capabilities of the LHC are very similar to what those of the SSC would have been. The SSC would have had higher energy, but it wouldn't have had as large a collision rate. So these two things more or less cancel each other out. Now, there's also some aspects of the LHC program that were not foreseen for the SSC, although I imagine they could have done it. For example, at the LHC, we're going to be colliding heavy nuclei in order to try to reproduce the plasma that filled the universe when it was a fraction of a second old. But yes, the SSC would have had very similar capabilities to that of the LHC.
The philosophy of naturalism holds that all that exists in the universe, all that exists at all, is physical existence that science studies. There isn't a separate realm of mental events, there isn't a separate realm of mathematics, there is just natural stuff in nature that science describes. If you believe that, you're a naturalist. However, there's a big division within naturalism depending on your view of the nature of time. And I'm going to talk about naturalism version 1, or what might be called timeless naturalism, which is the presently dominant view. It is the view that Einstein was reflecting from that quote. It is the view in which time either disappears or is just another dimension. In any case, there's no objective reality to our experience of the present moment within naturalism version 1. So let's talk about naturalism version 1, and then I will explain what's wrong with it, and then I will introduce you to naturalism version 2, which is intended to be a cure for the problems that arise in naturalism version 1. So is everybody with me? Okay. Naturalism version 1 started also with the Greeks, with the atomists, who had a conception that nature is nothing but atoms moving in the void. All sensory experiences we have, all sensations, all colors, all sounds, all hardness, all softness, all texture is all just a reflection of different ways that the atoms can be arranged and moved. In other words, atoms, which are, according to Democritus and Lucretius, eternal and unchanging, the properties of the atoms don't change, just like the properties on the list of the elementary particles of the Standard Model don't change in time. The charges in the different gauge groups of the quarks and the electron and the neutrino and so on don't change in time. We assume that the elementary particles have unchanging properties. They move according to laws which are unchanging in a space or a void which is also unchanging. Now that's had to be updated a little bit with general relativity, but that actually can be incorporated in the philosophy. This is the picture, atoms moving in a void, that all else is secondary, is emergent, as we would say. Secondary, as John Locke would have said. Emergent, as we would say in the present era. everything that's not the motion or the position of an atom or a collection of atoms is emergent, is a property which is not essential to the fundamental description of nature, but only emerges from collective properties of materials or atoms at a large scale. This is the philosophy that I think we all believe in, and I'm not going to be challenging its essential aspects, but I will be challenging it on one point, which is the relationship to the notion of time, as we see. And to say it very simply, if the laws are timeless, if the laws are not the result of some process of dynamics or some process of causation, they're inexplicable within the methods that we physicists have to bring to science. Because we can explain why this is the way it is. We can answer why something is the way it is when it's the result of some causal process that's evolved in time. The presumption that the laws of nature are timeless, are not phenomena that are influenceable or evolvable, means that they're outside of explanation. They're inexplicable. And that's the crisis of physics that we face.
This idea of how do we grow a galaxy? How do galaxies grow? And I want to start with the end, more or less. This is a picture that is a very famous picture, actually. Many of you may have seen it before. It's called the Hubble Ultra Deep Field. It's one of the deepest images of space that we've ever taken as humanity from the Hubble Space Telescope. And what you see here is an array of galaxies of different sizes, shapes, and colors and distances. You see blue galaxies that are forming stars actively, red galaxies that are evolving passively, and a finished forming stars. You see very young galaxies and old galaxies. And this is what the universe looks like today, more or less. And this is what we're trying to understand. How does the universe get from a fiery explosion in the Big Bang to this complex array of structures and galaxies that we see in the universe? What are the processes that drive this evolution? What are the important components that we have to integrate into any theory that can successfully explain galaxy formation and evolution? That's what I'll be talking about today. I'm going to start, however, by just talking about what galaxies are. What are they made of? What are the primary components that shape their behavior and images and their evolution? Next, I'm going to present what is our current best theories for a galaxy evolution, how they grow through this whole process of going from the Big Bang to the galaxies we see today. And finally, I'm going to describe how we've arrived at that story and that narrative, the techniques that we use, and the current research that's going on to learn more and more about the growth of these galaxies. This last part of the talk will be the most technical, but hopefully we can all come away with a better understanding of how the universe got to look the way that it does and how we know about it. So let's start. What are galaxies made of? When you think of a galaxy, the first thing that might come to mind are stars. And at a fundamental level, galaxies are collections of stars held together by gravity. But there are other really important components of galaxies as well. For instance, gas in galaxies. Gas is what forms stars. So if you don't have gas in your galaxies, you won't get stars. We also have dust in our galaxies. I'll talk more about this in a little bit, but dust is produced by stars, and it plays a strong role in the way that galaxies look. And it also plays an important role in the formation of planets and other solid bodies in the galaxy. And all of these three things we can observe with telescopes. There are also some more exotic components of our galaxies that nonetheless play a very important role in their evolution, despite the fact that we have to study them in very different ways. One of those is dark matter, and the last I'll talk about are black holes. And so all five of these things play a very important role how our galaxies look and how they grow over time. So let's begin now a little closer to home. If you take an image or look out into the sky on a very dark night, you might see something that looks like this. So this is a picture I took on the Big Island of Hawaii. I'll talk a little bit more later about why astronomers like myself spend a lot of time in Hawaii. It's not because of the beaches, or not only because of the beaches. Down here you see light from Kona, one of the towns on the island. If you look up, you see a lot of stars, and you see this kind of amorphous structure up here. And if I tilt my camera a little bit higher to cut out the light from the town, we see that that amorphous blob is actually the disk of our Milky Way galaxy. And so you're seeing billions of stars. Well, you can't see billions of them, but you're seeing a lot of stars out here. The stars are especially concentrated in this disk of the Milky Way. But you also see there are these dark patches along that disk. And the dark areas here are dark because there aren't a lot of stars outside of the disk. But the dark areas in the middle are not because of the lack of stars, they're because there are dust particles that obscure our view of the center of our galaxy. And these dust particles look something like this. They're very similar to dust particles that we have on Earth. Cosmic dust isn't that much different from the dust that we have on Earth, and that's because the Earth is made of particles like this that clump together and coagulate over time and build up large rocky planets and things like that in our universe. So dust plays an important role in getting us to where we are today, but from the point of view of studying our galaxy, it mostly obscures our view of the center of our own galaxy. Also, there's some people standing on the edges. If there are empty seats in the middle and you guys maybe want to squeeze towards the middle, it might make it a little bit easier for people to sit down. Because of this dust, it actually is rather difficult to study our own galaxy in optical light, especially looking towards the center. And so in some ways, it's easier to see the structure of galaxies by looking outside of our own and looking at galaxies that are relatively close by, but we can see from the outside. So if we could get outside of our Milky Way and look back at it, we might see something that looks like this. This is a galaxy called Messier 83. Creative name, based on the fact that it was the 83rd galaxy in the catalog of Messier. It also has a slightly more interesting name, the Southern Pinwheel, which is because, as you can see, it has this beautiful spiral shape. It has these spiral arms that look very similar to what we expect the spiral arms of our own Milky Way galaxy look like. This is a very typical grand design spiral galaxy, as we call it. And so what you can see now is that this galaxy has a disk. It has these spiral arms that we can see in dust, which is obscuring our view of the stars, which we see in blue here. The starlight is given in blue. If we zoom in on this arm of M83, we can see, again, these dust features tracing the spiral arms. We see the stars in blue, and then in red, this is hot gas that's being excited by the presence of newly forming stars in these regions. And so by looking at this hot gas, we can see how stars are affecting the gas around them and how that gas is forming stars and the role, the interplay of those two components of the galaxy. But again, this is hot gas that we're seeing that's excited by stars. Do you have a question?
So seeing that something that big at that distance, those red areas have to be huge.
They are.
How large are those?
Hundreds of light years across to 1,000 light years.
I mean, if you were there, what would you be seeing?
You would see, it would look very diffuse. So that's the thing, because these areas are very large and there's a lot of gas in them, but that gas is very spread out. So generally speaking, if you were there, unless you integrated for a very long time with the telescope, it would probably actually be very hard to see with your naked eye. But again, this is just the hot gas in the galaxy. There's also a lot of gas that's not being excited by stars, and this is the gas that's going to be flowing into the galaxy and forming new stars. And we can see that gas too by looking in the radio wavelengths. So it turns out that most of the gas in the universe is hydrogen, and that hydrogen emits this very, very faint signal in the radio. So if we zoom out from our picture of our galaxy, this is that whole galactic disk that I showed you. This is now a UV image of that galaxy. So all the stars are around here. And then much more extended in red, we have hydrogen gas around this galaxy that we can see with radio telescopes.
I'm fixating on those regions, but are there regions like that in our galaxy?
There are. Yeah, exactly. And much of what we know about the way that stars form from gas come from studying nearby regions like that in our galaxy. One of the most famous is the Orion Nebula, which is in the belt of the Orion constellation, and that's one of the closest star-forming regions in our own galaxy.
So it would look sort of like that?
It would look very similar to that, exactly. It had big bubbles that are being blown out by the stars that are forming. So now I've talked about the three components of our galaxies that we can see easily in light. So we have stars, we have dust, we have gas. Now I'm going to move on to some of the more exotic components of our galaxies. The first of which is dark matter. Dark matter is an area of a lot of current research. It's something that we don't understand very well. We're not sure what it's made of. What we know about dark matter is that there's a lot of it in the universe. It makes up most of the stuff in the universe, at least the matter in the universe. And it causes gravity. It produces gravity, so it has mass. But it doesn't seem to interact with light at all. It doesn't interact with the electromagnetic spectrum at all, which is why we can't see it. That's why we call it dark matter. And sometimes I talk to people, and they don't like the idea of dark matter. They don't like the idea of there being something in the universe that we can't see. And that seems kind of fishy or made up, but the fact is that we see things or we observe things in our daily experience that we can't see directly all the time. If I look out the window of my kitchen into our garden, I can very easily tell if it's windy outside. And I can't see the wind, but I can see the effect of the wind on trees, on leaves, and so I can infer that there must be something driving these interactions that I can't see, and it's just the same way that we can infer the existence of dark matter even though we can't detect it directly. So do you have a question in the back?
Yeah. When exactly was dark matter discovered and how did it do it?
That's an excellent question. One of the ways it was discovered is by looking at the rotation curves of galaxies. No, that's an excellent question and well timed. Some evidence that there was something that was producing gravity we couldn't see has been kind of seen over the course of the last century, but most of the really conclusive work on this was done during the 60s and 70s, particularly by this woman named Dr. Vera Rubin. She and others looked at the rotation curves of galaxies. So they looked at galaxies, spiral galaxies like our own, and how stars were moving around them, because these stars orbit the centers of their galaxies much in the same way that our Earth orbits the sun. And it turns out that if you've ever taken a weight on a rope or something like that and swung it around your head, you'll find that the faster you swing it, the more it pulls, and the harder you have to pull it back to keep it from flying away. And in a similar way, the faster stars are moving around the center of a galaxy, it takes more gravitational force to hold them together. So by looking at how quickly the stars are moving around these galaxies, we can infer how much gravitational force is holding them in and how much mass it would take to produce that gravitational force. And what we see is that when we measure the velocities of stars in these galaxies starting in the center and moving our way out, that the velocities increase as you go out, and then they stay very flat as you move over toward the edges of this galaxy. However, if we just count up the mass that we can see in stars, gas, dust in these galaxies, and say how much gravitational force should that create, how high velocities of these stars should that allow, we get a curve that looks like this red curve. And so these stars are moving much faster than we expect, which means that there must be more gravitational force holding them together than we realize. And that is one of the primary pieces of evidence we have for the existence of dark matter. Question in blue?
Does it seem that the stuff that we can see is more concentrated in the center?
That's exactly.
So why, if it's gravitational, why is there so much out there?
Right. That's an excellent question. I'll come to that a little bit more in the talk. But it basically, because the normal matter, what we call baryonic matter, can interact with itself in a way that dark matter can't. And it's able to emit light. The baryonic matter can emit energy and lose energy, which allows it to come towards the center of the galaxy, whereas dark matter has no way of doing that, and so it stays out on the outskirts.
Yeah. So these galaxies are spiral galaxies, and intuitively, if the entire galaxy is spinning at the same speed, unexpected to change shape, what keeps it a spiral?
Excellent question as well. It turns out that these spiral arms are not necessarily long-lived. They don't just move around in a fixed, shape, but rather that they're constantly kind of forming and changing in time as these density waves kind of travel through the galaxy. So that's a good point. Maybe one more question on this
So
one.
you included gas and dust when you talked about the stuff you can see, but of course gas and dust doesn't radiate. How could they be sure that it wasn't just gas and dust that accounted for dark matter?
That's a good question. So gas does radiate. As I showed previously, we can use radio observations to get a very good idea of how much gas is in these galaxies. It also turns out that dust radiates as well. So as I said, the dust, obscures our view of these stars. It absorbs the light from these stars, but it can't just keep absorbing light forever. It has to emit light. And so it doesn't emit that light in the visible part of the spectrum, but it emits it far in the infrared. And so if we take images, actually, if I showed you those same clouds that I showed you previously in an infrared image, we would see those dark spots in the optical as bright in the infrared. And so by using those techniques, we can actually get a very strong measurement of how much gas is in these galaxies. And in particular, it turns out that dust in particular is only about 1% of the mass of the gas in the galaxy typically. But this isn't our only evidence for dark matter either. Another very strong piece of evidence for dark matter comes from looking at galaxy clusters. So just as a galaxy is a collection of stars moving together, a galaxy cluster is a group of galaxies moving together in the same gravitational field. And so what you see here is an image of a galaxy cluster. Each of these kind of fuzzy things is a different galaxy. And we can, just as we can measure the motions of stars in a galaxy, we can measure the motion of galaxies in this galaxy cluster. And just as they do in the case of galaxies, we can see these galaxies and clusters are moving way too fast for the amount of gravity that we see to hold them together. If there were only stars and gas in these clusters, then those clusters would immediately just fly apart as everything moved away. And so that, again, provides a strong constraint that the vast majority of matter in these clusters is dark matter. But one more thing about these clusters is that we have the nice thing about these clusters is there's a second independent way to figure out how much mass is in them that doesn't rely on the motions of things. And that's because, according to Einstein's theory of general relativity, that mass actually distorts space and causes light to travel in bent patterns. And so what you can actually see a little bit in this image is you get these streaky things that look kind of like this. There's some down here, and if you kind of look, you can see that around this galaxy, or this cluster, there are all these kinds of streaks that all follow kind of a circular pattern. And those are all coming from galaxies and objects that are behind the cluster, and their light is being bent around this cluster and stretched out. And because we have the theory of relativity, we can very precisely calculate how much mass it takes to deform and warp the light from these galaxies in that precise way. And again, that gives us a very accurate measurement of the mass in these clusters directly, which agrees with kinematic information and tells us, again, that the vast majority of matter in these clusters and in the universe is dark matter.
Given the distances and masses, how much movement can we detect in 100 years even?
Right. It's a good question. So almost none in the plane of the sky. So we don't see this galaxy moving in this direction. But it turns out by using spectra of these galaxies, because if galaxies are moving towards us, the light coming from them gets compressed, like a Doppler shift. We can measure the shifts of those light. We can measure the velocities going towards us or away from us much better than we can measure the velocities tangentially to us. And so those velocities tell us that these galaxies are typically moving at around 1,000 kilometers per second. So it's huge velocities that we're measuring.
I haven't heard you, or maybe I missed it, I haven't heard you discuss the role of the black hole in all of this.
I had it, but that's the next slide. So I'll get there very shortly. Okay, one more question.
The dark matter. I'm assuming that it must be clustered towards the center of a galaxy.
So actually, for these galaxies, it tends to be more extended than the gas that we saw. As I was describing it, it's kind of what we call a dark matter halo, where most of it is much more extended than the stars in the galaxy.
But then, how is it affecting the rotation? If it's, I would think it'd have to be clustered in one place to affect to have a total effect.
The main thing, so as you see here, so in clusters, it's a little bit different, and it is more centrally concentrated in clusters. But but here, what you're seeing is that in the inner part of the galaxy, our measured and our calculations agree very well, and that's because most of the mass in the center of the galaxy is stuff that we can see from the stars. It's as you move out farther from the galaxy that these start to diverge, which is because the dark matter is much more extended. So in the centers of galaxies, you're mostly dominated by the gravity from stars, except for an effect of black holes. I want to move on just because there's a lot of things to get through, but there will definitely be time for questions at the end. So we have these clusters. Now I want to turn to that final component of galaxies that I mentioned, black holes. And black holes, we expect, are produced from the deaths of very massive stars. So when a massive star has a supernova, the very most massive stars may form a black hole upon their death. And so that's we can try to produce that in simulations and things like this. But our strongest observational evidence for black holes actually comes from observations of the center of our own galaxy. And if you zoom in on the very center of our Milky Way galaxy, what you see is that right in the middle there's a very dense cluster of stars. There are a bunch of stars very close together, moving around very quickly. And there's been some different teams that have been studying this cluster at the center of our galaxy for a long time. One of the major ones is at UCLA, led by Andrea Ghez. And this team, for the last 20 years, has been taking images of the center of our galaxy and the stars that are closest to the center of that cluster several times a year over the course of the past 20 years. And because these stars are so much closer than those, the other galaxies, we actually can, because we have very fine images of these stars, we actually can detect the motion of these stars over time. So when you combine these images taken over 20 years, and you track the stars over time, what you see is these stars are moving around the center of the galaxy. And in particular, when the stars get close to the very middle, they do some strange things. They move very quickly. And so by studying the motions of all these stars, it's become very, very clear that most of the stars at the very center of our galaxy are orbiting around something that we can't see. And in fact, we do see a little bit of radio emission from this object, but we don't see it. It's definitely not a star. And in fact, we can measure from these orbits exactly how much mass it would take to make these stars move in the way they do, and it's about 4 million times the mass of the sun. And because these stars get so close to that center, we can very precisely say how close together, how dense that mass is. And the only way to get 4 million times the mass of the sun in an area that small is by having a supermassive black hole at the center of our galaxy. And it turns out that we can look at other galaxies and look at the stars at the center of those galaxies, and we can see similar things. Or we can look at the motions of gas in the centers of some galaxies. And again, we see that most galaxies, at least massive galaxies that we can see around us, all have a supermassive black hole at their center. But we can only see these kinds of effects on galaxies that are fairly close by, where we can actually get a really nice view of the very center of those galaxies. But it turns out that we can also learn about black holes at the centers of other galaxies that are much farther away, but they're a slightly different type of black hole than in ours. Our black hole is a very passive black hole. It doesn't seem to be sucking up very much matter, and so that's because these stars, even though they're getting relatively close to it, they're not actually crossing the horizon that would cause them to be disrupted and accreted by this black hole. However, we know that we believe, I should say, that black holes are created from the deaths of massive stars, and these black holes start with masses that are 10 or maybe 100 times the mass of the sun. So in order to get from there to 4 million times the mass of the sun, these black holes have to grow over time. And the way that black holes grow is by absorbing matter, which adds to their mass and causes them to grow. So we know that even though our black hole is not absorbing a lot of material right now, it must have absorbed it in the past. And when black holes absorb material, they look very different. They look something often like this. So there's a class of black holes called quasars, which are not fundamentally different from black holes like our own, other than the fact that they are in the process of accreting material. And so when you get a lot of material close to a black hole, what you find is that this material that starts out very dispersed has to get squeezed down to a very small region in order to fall into the black hole. And when it does that, when you squeeze that material, frictional forces operate among everything, trying to squeeze down to the center, and that material, that gas, heats up. It heats up to tens or hundreds of millions of degrees. And so that produces such hot material that it emits a lot of light that then we can see from very far away. So again, we can't see the black hole directly, but we can see very, very hot material around these black holes out to very long distances. Do you have a question about that?
Black holes occur anywhere else besides the center of the galaxy?
Good question. So as far as we know, galaxies have supermassive black holes in their centers, and generally they'll only have one supermassive black hole unless you had two galaxies that recently merged together, and then their black holes, the black holes will eventually merge themselves over time, but if there's a very recent merger, you could have multiple ones. We also expect, and we see that there are smaller black holes, ones that are more like the 10 solar mass size that I described earlier, that it can occur anywhere in the galaxy, wherever a very massive star has died. But I want to return for a moment just to this, this accretion disk, as we call it, that is the very hot material around these black holes. And because it's this accretion disk that is part of the motivation for a recent, very famous image that some of you may have seen of a black hole that looked like this. This, if you haven't seen it, is an image from the movie Interstellar. Somewhat famously, this image is the result of an extremely state-of-the-art simulation of what a black hole might actually look like if you encountered it in space. And what you're seeing here in black is the edge of the black hole, the edge at which once something falls into that, you can't see it anymore. It's in that black hole forever. But as you see here, there's also this disk of very hot material spiraling around, heating up as it tries to fall into the black hole. And what you're seeing up here and down here is not actually stuff that's above and below the black hole. Again, as I mentioned, when you have something very massive, it warps light. And so if you look up to the top of the black hole, what happens is that the light actually bends down, and you can see the back of the accretion disk by looking over or above the black hole. And so that's why you can see these look like mirror images of each other, because you're seeing the same disk from above and below as that light is being warped. And so now if you pick up Interstellar on DVD, and you're watching it with family and friends, you can pause it right here and talk for 5 to 10 minutes about the physics of this, and I'm sure they'll really appreciate that a lot. Question?
What would it be like inside a black hole?
That's an excellent question, and I have no idea. We know a lot about what it would be like to kind of approach a black hole, and there are a lot of really interesting effects that happen there. But inside a black hole, it's very unclear.
I was wondering about the merging of black holes.
Mm-hmm.
Well, I've heard of black holes that are similar to like binary or trinary
Yeah.
star systems.
Yeah.
Would that be how a black hole would merge?
Exactly. So what you would expect is that if these galaxies merge, you'd have these two, each of them would have a supermassive black hole. It would eventually work their way to the center of the new kind of merged galaxy. And then they would, as they got closer, they would spiral into each other. And then it turns out because of what we call gravitational waves, it would slowly get closer and closer and closer and closer, and then would merge. And it's the gravitational waves from that kind of event that is another thing that people are trying to be able to study with new types of technology. One more question.
Stephen Hawking said something that, there's a lot of stuff that Stephen Hawking says that I don't fully understand. One of them was that because our universe itself is bounded but infinite, no edges but infinite, there is an argument by which it can be considered that we are inside a black hole. Can you say something about that?
I can say that it's very interesting, and that Stephen Hawking is a lot smarter than I am. So I'd say it might be, and if I go back to get a philosophy degree, I'll probably think a lot more about it.
I think maybe we better hold questions.
Yeah,
maybe
maybe
we'll let Ryan get through the material.
Sure thing.
Prepared here.
But now, so that's how are we doing? Is this? I might have. Did I just lose my? No, that's good. Cool. So just to recap really quickly, these are the primary components of galaxies that I've described to you: stars, gas, dust, dark matter, black holes. These are all really interesting things in and of themselves. But now I want to present to you our current understanding of galaxy evolution and how each of these things plays a role. So I'm going to start now at the very beginning. And this is an image of what the universe looked like very soon after the Big Bang. It might be hard to understand how this is an image of the universe, but what this really is a map of the temperature of the universe at different places. So there are red areas where it's hotter than average, blue areas where it's colder than average, and you can see that there's some distribution and variation of the temperature of the universe soon after the Big Bang. And this image, and again, it's an image, this isn't a simulation, this is an image of what the universe would have looked like if you imagine the universe to be, say, a 60-year-old human being. This is an image of what the universe looked like when it was about 14 hours old. So, not even a day old. This is a universe in its extreme infancy. And what you're seeing here is that soon after the Big Bang, as the universe was expanding, quantum fluctuations caused certain areas to have a little bit more energy or a little bit less energy. And as the universe expanded, those fluctuations got stretched out over time. And that's all I'm going to say about quantum mechanics for the remainder of this talk. What happens is that, so these quantum fluctuations start very small, and they're actually still very small here. I should say, for starters, that this image, the reason we can see this image is because it is imprinted on what we call the cosmic microwave background. This is light that was emitted soon after the Big Bang. It's kind of this last afterglow of the Big Bang that then has been traveling through space. And if we look at the sky in radio frequencies using radio telescopes, such as this is a radio satellite, actually, that's in space, to observe the radio emission from this Big Bang, we can make maps that look like this. This image has been generated to really show you which parts are hotter and which parts are colder, but it turns out that the variations between these regions are extremely small. So if green here, which you can't see very much of, is the average temperature of the universe during this time, then the very reddest areas you can see are 1,000th of 1% hotter than that average. And the bluest areas you can see are 1,000th of 1% colder than that average. So if you were in the universe, you would feel very strongly that everything was exactly the same everywhere. But that's not the case. There are actually these very, very small variations in the temperature of the universe. And it turns out that those are extremely important because these temperature variations correspond to density variations. So these hot parts of the universe are a little bit denser than average. The cold parts are a little bit less dense than average. And if you're denser, that means you have more mass and you produce more gravity than an average part in the universe. So if you're sitting in a very dense location, you have more gravity than your surroundings and you pull more stuff towards you. And so you get bigger over time. If you're sitting in an underdense location, you have less gravity and so you lose more stuff over time. And so it's kind of like capitalism, and that the rich get richer and the poor get poorer over time. Sorry, I apologize. But it turns out, that's a really important effect because it is these tiny, tiny fluctuations at the beginning of the universe that will grow and develop to all of the structure that we will see later at the end of the universe. And so the only reason I show you this here is that these are the seeds of all the galaxies that will form over the course of the universe. And now, sorry, I need to keep going just to have any hope of finishing in a timely manner. So now I want to show you now simulations of what happens when you start with a very, very slight distribution of densities, and then you evolve that forward in time. So if you take dark matter and gas in the early universe, so remember that early universe is mostly dark matter with some gas kind of along for the ride. You give it these slight differences in density, and then you just let gravity do its thing. What you see is something like this. This is a simulation of dark matter in the universe that starts soon after the Big Bang. So it starts with a mostly uniform cloud of dark matter, but with areas that are slightly more or less dense than others. And what you can see is that these density fluctuations grow, and they keep getting bigger and stronger. And they form these filamentary structures over time. In fact, we call this the cosmic web. And again, there is also gas in the universe besides dark matter. It's been neglected here because the dark matter is producing most of the gravity, and so on these large scales, it's really only dark matter that matters for determining the structure of the universe. But you can imagine that everywhere you see dark matter, there is also gas. And wherever the dark matter is flowing, gas is flowing right along with it. And so you see that these dark matter is it's forming these filaments, and gaseous filaments. It's flowing along these filaments into the centers of what will become galaxies. And so over time, these lumps, whatever there was a big lump of dark matter, continues to grow larger and larger. Gas and dark matter flow along these filaments into the centers of these future galaxies, and they continue to get more massive and start to form galaxies over time. And so the important things to take away from this simulation are that dark matter and we expect gas form these filaments that allow them to bring new material into galaxies and allow them to form. And also that they form clumps. So these filaments are really a bunch of clumps of dark matter and gas as well. And what we pull out of these simulations, one of the most important things that we pull out is what the distribution of sizes of these clumps looks like. So you can, this is a simulation that's zoomed in on this area here, which will eventually become a very massive galaxy. But if you zoomed out, what you would see, and you can already see to some extent here, is that there's a very small number of these very massive clumps, and there's a very large number of these very tiny clumps. And in between, there's a continuum of clump sizes. And again, when we have a big clump of dark matter like this, we call it a dark matter halo. And so there's a distribution of dark matter halo sizes that eventually we expect will correspond to a distribution of different galaxy sizes. So we can measure the size distribution, what we call the mass distribution of dark matter clumps in these simulations, and then we can make a graph of how many clumps of each side we see. So this is the mass of your dark matter halo here, and how many of the halos you see of that mass on this axis. And we get something like this from simulations. A very smooth distribution where there's a lot of low mass halos and a few large mass halos. And because each of these halos has about 20% of its mass in gas, we can look at the distribution of gaseous clumps in this simulation, and it should look something like this. Looks just like this curve, except shifted down because there's not very much gas compared to the dark matter in the universe. And then if you imagine that all of that gas gets converted into stars, then when we go out and look at galaxies and measure how many stars are in them, we would expect to see a distribution of stellar masses that looks just like this line, because all of that gas just turned into stars. But when we do this, when we take surveys of galaxy masses, we get a curve that looks very different. It looks like this. And there are a couple things to point out about this curve. One is that everywhere this yellow curve is below the white curve. And that means in no kind of galaxy is all the gas turned into stars. There's always only a fraction of the gas that turns into stars. And secondly, this curve looks particularly different at the low mass and the high mass ends. So as you move to low mass halos, these galaxies are very inefficient of turning gas into stars. And also in the high mass halos, they're especially inefficient at turning gas into stars. And we can understand this because of what we call feedback. Now, feedback is what we call the effect that whenever you put gas into a galaxy to try to grow it, it turns out that a lot of energy gets released, and that energy blows the gas back out of the galaxy and cuts off the growth of the galaxy. And I said that very abstractly. Specifically, what I'm talking about is particularly at this low mass end, there's what we call stellar feedback. So again, if you bring gas into a galaxy, you form some stars. Some of those stars are going to be very massive and very hot. And the light from those stars is enough to ionize and heat the gas and push the gas away to some extent. But even more so, when those big stars die, they have supernovae, which explode the gas and throw it out of the galaxy. And so as soon as you start to form stars, you're going to get some hot stars, you're going to get some supernovae, and then the gas will get thrown back out and you cut off your star formation. And we can simulate this by considering a simulation that's now not just dark matter, but it includes gas, it includes what happens to that gas as it forms stars. And so it's color-coded now by temperature, so red is the hottest gas, green is warmer, purple is cold. And what you see, you're going to see these same filaments that we saw in dark matter, where gas is flowing into a future galaxy along these filaments. But every time it flows in and forms some stars, there are going to be some explosions and things like that that heat gas and throw it out of the galaxy. So it's turning red, so it's getting hot, and it's being thrown out of the galaxy. And so if you let this evolve over time, more and more gas flows in, but every time you bring more gas in, you throw more gas out. And so at the end result is that this galaxy is very inefficient at turning that gas into stars. Most of the gas ends up in this hot cloud of gas around the galaxy. And of course, this is a simulation, but we can see similar effects in the real universe. This is an example of a nearby galaxy that looks very much like our Milky Way. I should say our Milky Way is not doing what I just showed you. Our Milky Way is forming stars only very, very slowly, and so it doesn't have these violent explosions. However, this galaxy, MED2, one before M83 that I showed you previously, it looks like a pretty typical maybe disk galaxy here when we look at the starlight. So this is what we see in the visible spectrum when we're looking at the stars. But if we look in the X-ray, we can see hot gas. And if we look in the infrared, we can see dust that's kind of coming along for the ride of that hot gas. And what we see is that it's being ejected from the galaxy. So this galaxy that looks so normal in terms of its stars is ejecting these huge plumes of hot gas and dust from the galaxy that are being thrown out by the processes I described, supernovae, the radiation from hot stars, etc. So that's particularly important down here. So we can call this stellar feedback. Is very effective at cutting off galaxy formation on small scales. But it turns out that we need something else to explain galaxy formation and the cutoff at large scales, because as you move to more massive galaxies, you have more and more mass that can hold onto the gas and keep it from being thrown out of the galaxies. And so you need something more powerful than star formation to cut it off. And this is an area that is very poorly understood currently, and is a major area of research. But the main candidate, we believe, is feedback from black holes. And I just want to remind you, this is that artist's impression of a black hole, or of a quasar that I showed you previously. And as a reminder, this accretion disk here is putting out tons of light. It's putting out much more light than the stars that I mentioned. And so it's even more powerful when it comes to heating gas and moving it around. But in addition to the light from this accretion disk, you can see here that there's this jet coming out of the top and bottom of the black hole, coming out of the top and bottom of the disk. Now this jet is really not well understood. We don't understand why these black holes produce jets very well at all. But we know that they're incredibly powerful. So this is an image of a nearby galaxy called Cygnus A. You can see this jet that is shooting out of the galaxy, throwing these huge amounts of gas and producing these giant plumes. And I just want to bring this home. The power of this image is that this is not the black hole at the center. This is the entire galaxy at the center. And so the size of these plumes are huge compared to the entire galaxy. It's clear there's colossal amounts of energy required to produce these kinds of features. And so while we don't entirely understand how these jets are formed, or how they interact with the gas in galaxies, it's very clear that they have the power to potentially cut off galaxy formation in even very massive galaxies. All right. So now I've given you a picture of our current theory of galaxy formation, how we go from the seeds of galaxy formation to building these large structures that form galaxies, and then these stars that eventually cut off their own growth over time. Now I want to conclude this talk by saying how we know what I'm describing. And in particular, if you've noticed, I've shown you a lot of simulations. I've shown you galaxies in the local universe and said, oh, this is how the simulations kind of reproduce what we see in the local universe. But I haven't shown you really what the universe looked like early in times when most of the galaxies like the Milky Way were forming their stars. Because most of the Milky Way stars were formed billions of years ago. So if we want to know what the universe looked like or what the Milky Way looked like a long time ago, it's actually pretty easy. All we have to do is look back in time, which might not sound terribly easy. You may or may not be aware we don't actually have time machines currently. Sorry to burst anyone's bubble. So we can't just go back in time and watch the Milky Way form over time, though that would be pretty awesome. We can do something, however, that's almost as good. We can look at other galaxies as they form. In particular, we can see them forming because the farther a galaxy is away from us, the longer the light it takes to reach us. So you may have heard that light from the sun takes 8 minutes to reach us. So whenever you look at the sun, you're actually seeing how the sun looked 8 minutes ago, not how it looks this very second. Trippy, don't think about it too much. When you look at these galaxies that are billions of light years away, it takes billions of years for the light to reach us. We're seeing the most distant galaxies as they looked billions of years ago when the universe was very young. And so we can look out into the distant universe. We can look at the properties of galaxies as they get farther and farther away, and which also means that we're looking farther and farther back in time. So giga-years, these are billions of years, and the universe is about 13.5 billion years old. So these farthest galaxies, we're seeing them as they looked very, very early in the universe's history. And what we see is that if you move back to how the universe looked about 10 billion years ago, this is the average star formation rate in galaxies, and that the average galaxy like the Milky Way was forming stars very violently, very strongly at these early times. And so these are the galaxies, these distant galaxies that we want to study if we want to catch galaxies in the act of forming. And so for the remainder of this talk, I'm going to tell you how astronomers like myself are studying these distant galaxies to test our theories of galaxy formation. But now, as you might imagine, if you're looking at galaxies that are billions of light years away, these galaxies are going to be faint and small. And so they're hard to see. You're not going to see them with your backyard telescope. In fact, you need extremely powerful technology to study these galaxies. And so I want to start by describing a little bit of what that technology looks like. To start, you need a really big telescope or telescopes. These are my two favorites. They're the Keck telescopes in Mauna Kea, Hawaii. These are that reason why I spend so much time in Hawaii, in addition to the beaches. But what you're seeing here are these telescope domes that are much bigger than this room, around the size of the side of the building. And if you go inside them, these domes have giant mirrors that we use to collect light. And these mirrors are about 10 meters or 33 feet across. You can see here's a regular-sized human being in the foreground of that mirror. And the cameras that we attach to the back of these telescopes that actually detect and characterize the light that they collect are as big as a car or larger. So these are incredible feats of engineering that allow us to study the distant galaxies in the universe. So once we have some Keck telescopes and some instruments, we can take images of the sky, and very, very sensitive images of the sky, and we can see something that might look like this. This is an image of the sky in one particular patch of the sky that I'm very fond of, from my own research, actually. And you see there are actually a lot of galaxies in this image. They're a little hard to pick out here. Most of the stuff that you can see with your eye very clearly are not interesting to me at all. It might be interesting to someone, but almost all of these very large blobs are stars. And they're not large. The reason they're large here is not because they're physically large, but because they're so bright that they saturate the detector. And so pretty much all of these very bright things are stars in our own galaxy that, frankly, I'm not very interested in. You do see a couple of galaxies here that you can probably see from the back of the room. There's this little smudge here, this little smudge here. Those are spiral galaxies. But again, these are galaxies that are very close to us, and I'm not very interested in them either. The galaxies that I study look something like this, which you may not be able to see. You'll have to trust me in the back of the room. There's a point there. There's a dot. And in fact, there's not just one dot like that, but there are a lot of them. Each of these red circles corresponds to a distant galaxy that I'm currently researching to try to figure out how galaxies form over time and what they looked like during this time when they were actively forming stars. And I do want to point out real quick, there is one other thing that's very interesting to me in this image besides these galaxies. I told you that almost all of these very bright things are stars, and that's true. One of them is not a star. This one is a quasar. And so even though it's just as far away as these galaxies, it's 10 to 12 billion light years away, it looks as bright as the stars are in our own galaxy, and that's because it's around 10,000 times brighter than these typical galaxies at that distance. And so I'll come back to this in a little bit, but that's what makes these quasars incredibly powerful tools, both for affecting galaxy formation, but also for studying galaxies, as I'll get back to in a little bit. But what you might notice is all these little galaxy dots are very, very small. We can't image them in the kind of detail that we can for those galaxies close to us where you saw those beautiful plumes of gas coming out. And so we have to study them in a different way. And this is where it'll get a little bit technical, but what we do is we take all of the light coming from a single galaxy and we break it up by its wavelength. So we put it through a prism or a grating or something like that separates the blue light from the red light and everything in between. And then we can graph how much light there is at every frequency, and this is called the galaxy spectrum. And what you see is that this galaxy has light at kind of all these different wavelengths. It's pretty flat. But there are specific wavelengths where it has a lot of extra emission or a lot less. And it turns out that where the places where there's less are because light is being absorbed, and the place where it has more is because extra light is being emitted. And the reason it happens at specific frequencies is because these correspond to changes in the atoms in these galaxies. So you can get absorption if you have an atom in its ground state and a photon hits it and excites it to a higher state, that photon will be absorbed. If an excited atom decays to a lower energy state, then that will emit a photon, which causes emission like this. And because these electrons in atoms have very specific energy levels, that means that you can only get absorption or emission in very specific wavelengths of light coming from this gas. And each atom, each type of atom, has its own energy levels to the electrons. And so by looking at the wavelengths of this light, we can see what kinds of stuff is in this galaxy. And in particular, these are different absorption lines from heavy atomic species that I'll show you in a second. And this strong emission line here is coming from hydrogen. It's coming from what we call the Lyman alpha transition of hydrogen, which is the transition between the first excited state and the ground state. And that's a really important transition because it's kind of the fundamental transition of the atom, and hydrogen is the most common stuff in the universe. So you put those two things together and you can see that's why we get so much emission at this one wavelength. And wherever we see light with this wavelength, we know we're looking at hydrogen gas. But if we zoom in on the rest of this spectrum, what we see is that there are all these little wiggles that correspond to little bits of emission or absorption by different types of material in the galaxy. And so we can actually study the chemistry of these galaxies, because if there's a line here, that means there's nitrogen. If there's a bunch of lines here, that's iron. And all these other different signatures of different elements in these galaxies. And we can see what elements are there. We can see whether these atoms are ionized to calculate their temperatures. And so we can learn a lot about the physical properties of gas in these galaxies, which tells us how are the stars producing heavy elements and releasing them in supernova. How are these stars blowing gas around in the galaxy and heating it up and that kind of thing. And then we can also use these spectra to look at the motion of gas. So as I told you, when material is blown or moved, it has a velocity towards you, away from you, it changes the wavelength of its emission a little bit because of that Doppler-like effect. And so when we measure an emission line like this, the width of that emission line tells us about the breadth of the distribution of velocities. It tells us about the velocities of the atoms that are causing that emission. And in particular, this line here is one that corresponds to the locations of stars in the galaxy. And so the width of this emission line tells us about how quickly the stars in the galaxy are moving. And that's really important because if you remember when we talked about dark matter, it's the velocities of stars and galaxies that can tell us how much mass is in the galaxy. So looking at the width of these lines tells us how massive these galaxies are becoming over time. Another thing we can do is look at the location of these stars. I'm going to skip through some things because I know it's getting late. But also we can look at this Lyman alpha emission that I described, and you can see that it's much broader than the location of the stars. That means the gas is moving much faster than the stars, and in fact it's being blown out of the galaxies. And if you look at the images of the stars and the gas, you can see that gas is much more extended again. So again, we're probing how gas is getting out of these galaxies. But now the last thing I want to talk about, so this is useful because we can learn about the gas right around galaxies. But this gas is being lit up by the stars in the galaxy, and the stars aren't bright enough to show us what the gas looks like very far from the galaxy. So if we want to look about what the gas looks like on large scales in the universe, we have to use something different. And in particular, so this is again the simulation of dark matter in the universe. We expect that these filaments that we see in dark matter simulations also have gas that traces these same structures. And if we want to really test our theory of how this gas and dark matter is distributed, we need some way to look at the distribution of this gas and dark matter on very large scales. And you can't do that with the light from galaxies, but you can do it with the light from quasars. And so if you imagine you have this very bright quasar right here, one of the ways we can look for gas using this quasar is looking for absorption in the light from that quasar. Because if you imagine that we're standing somewhere over here and the light to the quasar is traveling towards us, it will pass through all these filaments of gas on its way to reach us. And every time that quasar light passes through a filament of gas, some of the light gets absorbed. And so what happens is that when we look at the spectrum of this quasar, as the light travels to it, it picks up these little absorption signatures every time it passes through gas. And so at the end of the day, we have a spectrum that has some areas with very little absorption that correspond to a region with very little gas. We have some parts of the spectrum that show a lot of absorption, and that corresponds to some area where it really passed through a thick filament. And so by using the information in this spectra, we can try to then reproduce what does the density of gas look like along our line of sight to the quasar. It turns out this is a really powerful technique. In fact, most of what we know about the distribution of gas in the universe comes from looking at quasar spectra like this and looking for absorption that tells us about the distribution of gas. Yeah, and it works really, really well. The only downside of this technique is that even though it's very precise, it only tells us about the gas right along this line. If we want to learn about the three-dimensional distribution of gas, we have to rely on the fact that either you have quasars every single place you look in the sky, which unfortunately isn't the case, or you have to find some way to image the gas that's farther away from this line of sight. In particular, we'd really like to learn about the gas that surrounds these quasars, because we'd like to learn how are these quasars themselves being fed by these filaments of gas. And so one way we can hope to do that, and one thing that I'm working on with some other researchers here, is to try to see whether if these quasars are emitting light not just towards us, but in all directions, then the light from this quasar could illuminate all this gas around it. And so if that emission is going to be very, very faint, because not very much of the quasar light is going to scatter off of this gas in our direction. But if we can detect it, we can hope to make a map of the universe that might look something like this, where everywhere that we see a quasar, we get this bubble of a region where we can probe the large-scale structure of gas. We can see how that gas is getting into galaxies, feeding stars, feeding quasars, and we can also test whether these filaments that we see in simulations really look the way they do in the real universe.
Yeah, I have a question about dark matter. It confuses the heck out of me. If I understood you correctly, most of the dark matter in the galaxy is external to the visible central part of the galaxy. It's outside.
Right.
Now, I've always understood that if I could transport myself to the center of the Earth and avoid burning up and being crushed by pressure, I would feel no gravity. Because I would be surrounded equally by Earth on all sides, and the gravity would balance out. So how can the gravity of the dark matter surrounding a galaxy have any effect on the whirl, speed, cohesion?
Right, good question. And the answer to that is that I think I spoke imprecisely earlier. So there is dark matter interior. It's not in a shell outside of the galaxy. If it was, it would have no effect whatsoever. Rather, it is throughout, and actually the dark matter is densest in the center of the galaxy. It's just that the baryons, the stars and stuff, are even more dense. So when you're close to it, the dark matter doesn't have an effect so much because you're dominated by the mass of other things. But it's only as you move farther out that the dominant effect is because of the dark matter. In the black?
So earlier in the talk, we spoke about gaseous hydrogen emitting radio waves.
Yeah.
And I'm wondering what the mechanism is that generates that.
That's an excellent question. It's one of the really interesting things that kind of about atoms that we learn, or things about chemistry that we learn from astrophysics, and that it turns out that this emission is emitted. So because it's radio waves, that means it's a very small energy gap between an excited state and the ground state or the bottom state. So if you have a large gap, you're going to see high energy photons in the optical or X-ray. If you have a small gap, you'll see them in the radio. And so it's a transition that's a very, very small energy transition, and it has to do with whether the spin of the electron, so electrons have spin, protons have spin. If those spins are aligned or anti-aligned, there's a very, very tiny energy difference between those things, and it has to do with a bunch of different quantum effects.
So it's not even electron shells, it's just different.
Exactly, it's just different spin orbits, and that's why it's a much smaller energy than jumping to a whole bunch.
Molecular versus atomic?
It is atomic, though. There are molecular transitions as well, exactly, that are also, most of what we see in the radio tends to be molecular transitions.
Yes. In our solar system, in the planetary region, including the Kuiper Belt, it's a disk. The Oort cloud is more or less spherical.
Sure.
What's the situation with galaxies? Is the dark matter sphere spherical, or is it the disk, or something else?
Right.
And finally, what about dark energy?
Okay, good questions. Yeah. So the answer to the first part of the question is yes. Actually, the dark matter is fairly spherical. Maybe not exactly a sphere. It could be a blade or this kind of thing. But yeah, it's roughly symmetric. And the reason that disks aren't is because, as I mentioned previously, gas can interact with itself in a way that dark matter can't. So gas tends to interact with itself and lose energy in such a way that it moves towards the center of halos and also flattens out. It picks one preferred direction where most of its angular momentum is and just forms a disk in that orientation. Dark matter doesn't have a way of shedding angular momentum or interacting with each other and forming that kind of structure, so it is a much more blobby halo in which in the middle you have a disk. As for dark energy, hugely interesting. It's in terms of the energy density of the universe, it's even more important than dark matter. But it doesn't actually play a huge role in galaxy formation for a number of reasons. One is that it acts on very large scales, so large compared to the size of galaxies. And also because of the way that these different components of the universe, like matter and dark energy, evolve over time. In our current universe, dark energy is kind of the most dominant component of our universe, but that's only been the case for the last few billion years. Prior to that, matter was the dominant component of our universe. And because most of these galaxies formed when matter was dominant, that's another reason why it doesn't play a strong role in their evolution. In the red shirt?
Do you know much about the role of statistical techniques in inferring the large-scale structure of the universe?
To some extent, yeah. So I think, so I mentioned there are a number of different surveys and things like that are working on things like that. One, I don't know if you have a question about a specific one. One thing that's really interesting, I think, is, I showed you the absorption coming from a single quasar. But if you do, you can't have quasars at every point in the sky, but if you do have a number of different quasars that are fairly close together, you can measure the absorption of these different quasars and try to correlate between them to map 3D structures. Also, even in individual quasar spectra, even if they're not close together, we can say, it's one thing to say, oh, this quasar spectra shows us that there's one structure here and another structure here. That might be interesting. But it's also just interesting to look at that spectrum and say, how many large structures and how many small structures are there? What's the distribution of those? And how does that compare to the distribution of dark matter halo sizes from simulations? So those are two techniques that are really important as well. Is that? Yeah.
So there's a delightful article in maybe the most recent Scientific American. I think it's about fossil galaxies, basically. So you mentioned that we can't look back in time for our own galaxy. But it strikes me that this is a way that, in some sense, we can. We can see these patterns of stars that have come in. And one of the things I'm curious, there seems to be many of them, so that there are many galaxies colliding with our galaxy, and you assume they all had massive black holes, and kind of wonder what happened to those massive black holes. Are they still scattered around, or are they all combined in the center?
Yeah, those are good questions. So, mostly the way that I study galaxy formation is primarily by looking, back in time, the way galaxies looked when they were forming. There's another, very different technique where people do look at our own galaxy and nearby galaxies in a lot of detail to try to, look at all the details and then try to extract how could we have gotten that way. And they're complementary techniques because we can look, for instance, at very small structures in our own galaxy and try to figure out sort of satellite galaxies, like you said, that might be orbiting our own galaxy and try to figure out what kind of formation scenario would produce a galaxy that has a lot of satellites versus one that doesn't. As for the black holes, so currently when we look at dwarf galaxies, a big question is whether these dwarf galaxies do have black holes or don't. Because they tend to not have a lot of stars and they're very faint, it's hard to, and because they're smaller, we would expect black holes of them are also smaller. So they're difficult to detect. So we're not, I think, entirely sure how that works out and whether it is all galaxies, even very tiny ones that always have these supermassive black holes, or if it's only the massive ones that do, and if that's the case, why don't they have them? I think those are open questions. And back?
Why is your Big Bang picture not circular?
Good question. Honestly, so the way they project, so truly this picture, it's of the whole sky, so it would be like the inside of a sphere, looking up in any direction coming from the Earth. But because it's hard to show that on a 2D screen, they project it like this, just like when you look at a map of the globe. That's truly a sphere, but you try to project it in some way that kind of maintains some kind of sense. So the idea is, here, this is kind of the horizontal, like the equator, and this is kind of the North Pole, South Pole. Even those things are arbitrary in terms of the universe as a whole, but in terms of our view of the universe, that's what. And actually, it turns out the way they decide on the axis for this is actually where the disk of our galaxy would be, right down the middle here. So looking up, it's looking out of our galaxy, or down is out of our galaxy. the question about if the universe is infinite, kind of what does it mean to be expanding and that kind of thing if it's already infinite? So that's a complicated question, and there are a lot of different elements to it. One is that you can have different sizes of infinities. And so actually when we do math, we find all the time that you can have this infinity and this infinity, but this one can still be twice as big as this one, for instance. In some kind of, you have to do that in a well-defined way, and it's kind of counterintuitive. But something can be infinitely large, and still on some level get larger. But yeah, usually what we're talking about, we're going to talk about, say, the observable universe, which is only that stuff that's close enough to us that the light has had time to reach us over the entire history of the universe. If it's farther away, then the light that was emitted even, when it first formed hasn't had time to reach us in the entire history of the universe. So usually, yeah, it's often helpful to just talk about the observable universe, and we can clearly say that the entire observable universe should have been compacted down to a single point. And so that's what we would call the Big Bang, more or less. Does that answer your question? Yeah, cool. In the far back?
Yeah, in passing you kind of alluded to the fact that gases form planets, but you haven't indicated how significant the planet attracts gases are to the whole concept.
Right, that's a good, that's a good point. I haven't talked really about planets at all. That's mostly because they actually don't make up very much of galaxies, even if we're now finding that most stars seem to have planets around them. But still, even in our solar system, even with our 8 planets, the planets only make up about 0.15% of the mass of our solar system. So it's really not significant in terms of how the whole galaxy forms. But yeah, this idea of how planets attract gas and all that is very interesting for figuring out how planets get atmospheres and that kind of thing.
I'm aware of time, so let's just take one more question.
Yeah, one more. Better make it a good one. Go ahead, please.
Okay, dark matter, 2 questions.
Yeah.
Well, 2 parts. You've got the periodic table.
Yeah.
Different elements.
Right.
Where does dark matter show up?
Excellent
And
question.
what are the parts to an atom is made of this and that? What's dark matter made of?
Right, excellent question. That's a major area of current research. Things like the collider at CERN, they made like the Large Hadron Collider. You've seen this documentary, Particle Fever. It's really, really interesting. It tells you about how particle physicists here on Earth are trying to learn more about the kind of exotic types of matter that we're starting to see some evidence for in space. The main question is, so the dark matter would not fall in the periodic table because things on the periodic table are all actually pretty similar to each other. They're all made of electrons, neutrons, and protons. We believe that a dark matter particle, whatever it is, would be something that is not made of protons, neutrons, electrons, because those things all interact with light. There are other types of other types of particles we know of that we learn of from particle physics and from these colliders that are not, those protons, neutrons, electrons. And so we do have a lot of evidence that there are these other types of massive particles that, could potentially be, are similar to what a supposed dark matter particle in certain ways. But currently, none of the particles that we've detected seems like it would be an acceptable solution to generate the effects that we see from dark matter. So still working on it, both from observations in space and experiments on the ground. So thank you guys so much.
Thanks for coming. Thanks again for those of you who donated both today and who have donated, will donate online and elsewhere. And I hope to see you again next year across in GTV, just across the way there.
Thanks very much for filming this. Oh, yeah, no problem.
Connection between the physics of the very small, the microphysics, and the physics of the very large, macrophysics and cosmology. And I'll try to bring out those connections between the two during the course of this talk. So in our journey towards the very small and towards the very large, we're going to meet a number of ideas which I would just like to mention to you as we get started. So one of the issues, in fact, the primary motivation for building these large particle accelerators is to understand what matter is made of. And in fact, we have a theory for how the visible matter in the universe is constructed, which I'll describe very briefly later on. This theory has certain things which are missing elements which we hope to find with the LHC. Also, we think that there is physics beyond what we call the standard model of particle physics. For example, the astrophysicists and the cosmologists tell us that something like 80% of the matter in the universe is some form of invisible so-called dark matter, which they can't see with their telescopes. But I would claim that we, with our telescope, do have a chance of seeing this. As I mentioned, we hope by this sort of study of fundamental physics to cast some light on the way in which the universe evolves. This is because when we make our collisions in this sort of particle accelerator, we are reproducing the sorts of collisions that took place when the universe was a fraction of a second old. And I'll explain this in a little bit more detail later on. One of the sorts of issues that we can address in this way is where the matter in the universe originated. You look around you, you see matter. You see radiation. You don't see antimatter. Now, we physicists know that every matter particle is in principle accompanied by an antimatter particle with very similar but opposite properties. Where did all that antimatter go? Maybe laboratory experiments can answer that question. The universe is kind of big and old. How did it get to be that way? Maybe by understanding the early history of the universe better, we can answer the question. We know that there are 3 dimensions of space. Are those all that there are, or are there perhaps more dimensions of space? This is a possibility which is suggested in many theories of microphysics, and that might also cast some light on the early history of the universe. So the Large Hadron Collider, the LHC, the project which I showed you on my first slide, its principal jobs are to ask, and the time when physicists finally got themselves convinced that matter was made out of atoms, Thomson, whom you see here, discovered that actually atoms were divisible and they had these electrons inside them. The apparatus that he used to show this is much like a traditional TV set. I used to be able to omit the word traditional, but nowadays, with all these plasma displays and so on and so forth, I have to sneak in the word traditional. So the old-fashioned TV sets had this sort of conical thing sticking out the back. And this conical thing sticking out the back was actually a primitive particle accelerator. It would do the same sort of job that Thomson's apparatus did. It would take an electron out of an atom and then accelerate it using electric and magnetic fields to strike the screen at the front. And then the image on the screen, well, that was what you saw. So particle accelerators are much like that. We extract electrons or protons out of the interior of atoms. We accelerate them, and then we either hit a fixed target or we hit these particles against each other and try to see what is produced. Now, many of the different types of elementary particles were first discovered in the cosmic radiation. As you probably know, the Earth is bathed in energetic particles coming from outer space. In fact, these were discovered a little under a century ago by Mr. Hess here, who's going up in his balloon. He went up in his balloon and discovered that up in the upper atmosphere there were all these charged particles raining down. Subsequent experiments showed that these particles produced many other different types of particles. The study of these things was a little bit haphazard in the first half of the 20th century, which is why sometime around the turn of the century, big accelerator laboratories were first constructed. And in particular, CERN, the European laboratory where I work, was founded in 1954, in order to study in more detail, under controlled laboratory conditions, the natural phenomena of elementary particles. Let me just mention one particular discovery that was made initially in cosmic rays and then followed up in particle accelerators. So I already mentioned antimatter. So this was actually first predicted theoretically about 80 years ago, and shortly afterwards, the first particles of antimatter, the positrons, the antiparticles of electrons, were discovered in cosmic rays, and hopefully answer at least some of these questions. So let's start off by looking inside matter. Now there's sometimes a misconception, which I'd like to clear up. What we study with these particle accelerators is not some sort of abstruse stuff. We're actually discussing the structure of matter, the same matter that you and me and these roses are made of. And I think that we physicists sometimes fail to convey the wonder of the fact that all the visible matter in the universe is made up out of the same very limited number of constituents, which is really quite remarkable. All the variety of stuff that we see in nature is made up out of a few very small constituents that we can study in the laboratory. So you all know that matter is made up out of atoms. Atoms consist of electrons circulating around nuclei. You can think of nuclei as being a little bit like the sun in the center of an atomic solar system. Now, in the first half of the 20th century, it was realized that those nuclei could all be made out of two particles, the proton and the neutron. And for a while, physicists thought that protons, neutrons, and electrons were basically all the elementary particles that there were. In fact, what happened in the second half of the 20th century was people first of all realized that protons and neutrons were not alone. There were many other similar types of nuclear particles. And then they understood that these nuclear particles could all be understood in terms of a very small number of particles called quarks. So the frontiers of our current knowledge are electrons and similar particles, and inside the nucleus, quarks and the particles, the gluons that hold them together. So our job now in particle physics in the 21st century is to go beyond what was achieved in the 20th century and try to understand in more detail just exactly what these fundamental particles are, and also to understand the forces between them. Some of the forces are relatively well known. For example, electromagnetism, which holds those electrons in orbit around the atoms. Gravity, of course, that's also well known, but some of the other forces may not be so familiar to you. So I thought I would just briefly review with you one or two aspects of the search which revealed to us, or the searches that revealed to us some of these elementary particles. In fact, the first elementary particle to be discovered was the electron. It was discovered right towards the end of the 19th century. In fact, it's sort of ironic that just around here is Anderson with his apparatus that he used to discover these first antimatter particles. So these things have the same mass, but the opposite charge as conventional electrons. Now, for many, many years, the existence of antimatter was a sort of academic curiosity. But in fact, now they're used regularly in medical diagnosis, and this is actually something that I'll come back to towards the end of my talk. So that's just an example of how even totally abstruse discoveries might actually turn out to be useful for real people like you, as opposed to physicists. Okay, so these studies, first of all with cosmic rays and then followed up in more detail with particle accelerators, led us to what we call the standard model of particle physics. And I'll just summarize it very briefly on this slide. So what you see here are the fundamental particles of matter. So we already met the electron. For a reason which we don't understand, the electron is followed by two heavier particles, very similar but just larger masses. Over on the left-hand side here, we have the quarks. These are the constituents of nuclear matter. In fact, the regular stable nuclei could be made up out of just two different types of quark called up and down, but in cosmic rays and in collider experiments, 4 more quarks have been discovered. We don't know why there are 3 electron-like particles. We don't know why there are 6 quarks, and that's one of the big mysteries that, well, we might get some insight from the LHC. The bottom half of the slide, you see the 4 fundamental interactions. Gravity and electromagnetism, and then 2 forces that act inside the atomic nucleus. The strong force, which holds nuclei together most of the time, and the weak nuclear force, which causes some particles to decay. It's actually the interplay between these 2 forces which enables the sun to shine. So although we don't necessarily like the idea of nuclear forces, in fact, they're absolutely essential for our existence. So what you see on this slide contains enough information when you go through the physics, go through the maths, to explain all the visible matter in the universe. And for that reason, I like to refer to it as being the cosmic DNA. So I said cosmic DNA, in particular, all the stuff in the universe, the visible stuff in the universe, is made out of what you saw on the previous slide. So here's a picture. So what I want to do today is to introduce to you what I think is the world's most powerful microscope and also the world's most powerful telescope. Now, when you think of microscopes or telescopes, you think of sort of peering through some eyepiece down like that, or peering through some sort of eyepiece up like that. You probably don't think of what you see on this slide here. This slide is a picture of the region of Geneva in Switzerland. Those things at the back there, for those of you who are native Illinoisans, those are mountains. And, okay, so that's the Mont Blanc. This is downtown Geneva over here. This is the local airplane accelerator, otherwise known as the airport runway. And here, outlined in red, you have the location of our microscope stroke telescope. So it's a particle accelerator. It's about 27 kilometers in circumference, and on average, it's at a depth of about 100 meters. So in fact, from your airplane, you don't see very much. You might see 1 or 2 surface buildings, for example, this one over here, but most of the real action takes place about 100 meters underground. So what I would like to do in the course of this talk is explain why we've been building this thing, what science it is supposed to do, and I'll discuss also the progress that we've been making in this project, and in order to forestall some questions, what use it all is. So I thought I'd start off by sharing with you a reproduction of a painting by Gauguin, which I had a copy of the wall on my office when I was a graduate student, embarrassingly many years ago. So what these people here are asking are very fundamental questions. Where do we come from? What are we? Where are we going? And what I would like to argue is that the project, the Large Hadron Collider at CERN, which I showed you briefly on the previous slide, that the aim of this project is precisely to address these questions from the point of view, obviously, of a physicist. Concretely, what we try to do with projects such as our accelerator at CERN and the Fermilab accelerator just outside Chicago is we try to understand what the universe is made of. We also hope to understand the evolution of the universe, which could enable us to understand where we come from. And maybe we'll also learn a little bit about what might happen to us and to the universe in the distant future. So that's the aim of the project, which, as you see, is